Okay, welcome back to part 2 of Lecture 12. And again, I'm splitting these up so I don't load humongous files up to YouTube and cause any clogging up of the works. So, now we'll take a look at a simple minimization problem in Excel. So here we have M&D chemicals, and they produce two products, let's say paints, that are sold as raw materials to companies well, let's call them some other products that they're sold as manufacturing to other manufacturing companies. And based on the analysis of the current inventory levels and potential demand, M&D's management is looking at certain production requirements. So let's look at this particular model. Our goal in this case is to minimize our total cost. Our decision variables are the amount of product A and the amount of product B. And the production cost for each one of those is $2 and $3. So we use a sum product to get our total cost, which is B5 to C5. And B5 and C5 have the cost of product A and the production cost of product B, respectively. And we multiply those by B14, the quantity of product A, and C14, the quantity of product B. And that'll give us our total cost. We're also subject to certain constraints. Total available time is 600 hours, and it takes 2 hours to produce product A and 1 hour to produce product B. We also have to have a minimum production of product A of 125 gallons and a minimum total production of 350 gallons. So here's our objective function. Let's take a look at our constraints. Product A provided is just going to be equal to B14, and the required amount of that is 125. Likewise, the amount provided of total production, products A and B, is 2, but we require 350. So a gallon of product A and 1 gallon of product B is not a feasible solution because it violates these constraints. It does satisfy the processing time constraint. We use 2 hours to produce the 1 gallon of product A and 1 hour to produce the 1 gallon of product B, for a total of 3 hours, and the hours available are 600. So this is the model we've got set up. So to provide the solution for the minimum cost production schedule, we're going to define our decision variables and, of course, the objective function. So the decision variables are the quantity of product A and the quantity of product B. And those are in cells B14 and C14. Our objective function is to minimize 2 times A, which is the gallons of product A produced, the quantity of A, plus 3 times the quantity of B. And that, of course, is in cell B16. And we'll go ahead and go to Solver. So again, we go to Data, go over to Solver on the far right, and here we have a dialog box. Our objective function is, as mentioned, B16, our total cost. our goal with this optimization is to minimize total cost. And we're going to do that by changing the quantities of product A and product B that we produce. And as we see here, that's in cells B14 and C14. Now we do have some constraints. So subject to the fact that B19 and B20, the amount of product A and the amount of total production provided is greater than or equal to the amount of product A and the total production that is required. So provided must be greater than or equal to required. Likewise, we have another constraint, and that is that the hours used be less than the hours available. We're going to use the simplex algorithm again. So we leave it at that. That's the one we use for linear. And I'll go ahead and click solve. And Solver does find a solution. And I'm also going to get a report with this. And the solution is that we take 250. We produce 250 gallons of product A and 100 gallons of product B. That satisfies our two provided requirements, and it also satisfies the hours used requirement or constraint. So our minimum total cost in this case is $800. $2 times 250 plus $3 times 100. So let's take a look again at our answers, our answer report. We find that the final value is 800, and we produce 125 and 350. We have slack in the total product A provided. In other words, we have 125, we produced 125 gallons more than we did to meet the minimum required. The other two are binding constraints. So both the total production constraint and the processing constraint, the time constraint, are binding. The requirement of at least 125 gallons of product A be produced is not binding. For greater than or equal to constraints, we define non-negative variables as a surplus variable. A surplus variable tells us how much over the right-hand side, the left-hand side of the greater than or equal to constraint is for that solution. Okay, and again, we've discussed the problem formulation and our objective function subject to the constraints. 1 times the quantity of A is greater than 125, 1 times A plus 1 times B is greater than 350, and 2A plus 1B is less than 600. And we had a surplus of 125 gallons in terms of the constraint on the minimum for product A. And here's some dialog capture for what we have done in Excel. And of course, we looked at the answer report as well, which told us we had a slack of 125 in our product A provided. Okay, let's take a look at sensitivity analysis, and we're going to use M&D chemicals again. So we'll go back to our model, and this time we'll do a sensitivity analysis. So I go up to Data, go over to Solver, going to minimize this, the constraints, click Solve. This time under Reports, I'm going to select Sensitivity. Click OK. And now I have a sensitivity analysis. In sensitivity analysis, the study of how changes in the input parameter of an optimized model affect the optimal solution. It's going to help in answering questions like how will a change in the coefficient of the objective function, in other words, the number of hours, the cost per hour, or the profit per unit, the quantities, the coefficient that go along with the quantities in our objective function will affect the optimal solution. So in other words, in this particular case, our coefficients are going to be the cost of producing product A and the cost of producing product B. $2 for product A and $1 for product B. So if we increase the dollar amounts, then that coefficient 2 times A or 1 times B will change. It might be 3 times A plus 2 times B if we go to $3 and $2. The other thing we'll look at is how a change in the right-hand side of the constraint will affect the optimal solution. So let's say we needed to produce a minimum of 375 units of total production. How would that affect our solution? So we see that in this particular sensitivity analysis, and the shadow price for a constraint is the change in the optimal objective function value if the right-hand side of that constraint is increased by 1. Non-binding constraints will always have a shadow price of 0. Making a binding constraint more restrictive degrades or leaves unchanged the optimal objective function value. On the other hand, making a binding constraint less restrictive improves or leaves unchanged the optimal object function. Shadow prices are symmetric. The negative of the shadow price is the change in the objective function for a decrease of 1 in the right-hand side. So here we see that if we increase the total production provided, we had a shadow price of 4. So that's going to increase our minimal cost by $4. So in the constraints section of the sensitivity analysis, the first column gives the cell location of the left-hand side of the constraint. The second column is the constraint name, and the third column is the value on the left-hand side of the constraint at optimality. And the fourth column gives the shadow price for each constraint. So a shadow price of 0 for product A provided shows that if we increase the required amount of product A from 125 to 126, it's not going to affect the minimum cost. because we're already producing 250. The shadow price of 4, if we change the constraint to 351 for total production, the cost of the production will increase by 4. In other words, the objective function will increase by 4. Shadow price of -1 means if we change the constraint to 601 available hours, then the objective function will decrease by 1. The sign of the shadow price depends on whether the problem is a maximization or a minimization type, and the type of constraint under consideration. When observing the shadow prices, the following general principle holds. Making a binding constraint more restrictive degrades or again leaves unchanged the total optimal objective function, and making a binding constraint less restrictive improves or leaves unchanged the optimal objective function. Okay, above the constraint section is the variables section. Columns 1 through 3 are the same as in the constraint section, and the fourth column is reduced cost. The reduced cost indicates the change in the optimum objective function value that results from changing the right-hand side of the non-negativity constraint from 0 to 1. The fifth column contains the objective function coefficient for the particular variable. In other words, the production cost. And as I mentioned, you can change it from $2 to produce a can of A to $3 to produce a can of A. And then the allowable increase and decrease indicate the change of the objective function coefficient for which the current optimal solution remains valid. So, of course, we set up our decision variables and our objective function, and we found the optimal amounts, 250 and 100. We went over shadow prices. We reviewed the sensitivity analysis report, which we see right here. We reviewed it in Excel, of course, rather than PowerPoint. And classical sensitivity analysis is based on the assumptions that only one piece of data has changed. If we want to see what happens if we have two or more pieces of input data that are changed simultaneously, in Excel the easiest way to do that is to, in other words, to examine the effects of simultaneous changes, is to make the changes in the model and then rerun it. Okay, let's look at some other cases here, and we'll look at these in more rapid succession. We'll look at an investment portfolio and transportation planning and an advertising campaign. So as an illustration of portfolio optimization, we have an example, Welty mutual funds. They have several investment guidelines. They have two industries. They invest in oil or steel. Neither one should receive more than 50,000 of the 100,000 available. The amount invested in government bonds should be at least equal to 25% of the steel industry investments. And the investment of the risky Pacific oil cannot be more than 60% of the total oil industry investment. So they get $100,000 and they want to invest it subject to those constraints. Here's the projected rates of return. And what we want to do is to maximize our rate of return on our portfolio given the particular constraints that we have. So our objective function is going to be, as we see right here, for Atlantic Oil, let's call that X1, the dollars invested in that. So it's going to be 0.073 times X1 plus 0.103 times X2, Pacific Oil, plus 0.064 times X3, Midwest, plus 0.075 times X4, Huber Steel, and then finally plus 0.045 times government bonds. And again, some of the constraints. Here's our functions. Let's take a look at how we set this up in Excel. So we've got our projected rate of return for each one of our investments. Then we have the quantity that we're investing in each one of the investments, and I'll change these to numbers. Well, we'll leave it as dollars, what the heck. So I just put a placeholder in of $1 for each one of them, and at that we have a total maximum return of 36 cents. And that, again, is just the application of 1 times 0.073 plus 1 times 0.103 and so on. So this is our maximum total return. This is what we want to maximize. This is our objective function. So this gray area is our decision variables, and the total max return is our objective function. We get that by multiplying the quantities for each one of the investments times the rate of return for each one of the investments. Additionally, we have some constraints. So total funds invested right now, $1 in each of the 5 is $5. We only have $100,000 available. So we do satisfy that constraint. And then with our funds invested, we have $2 invested in oil, the maximum $50,000. $2 invested in steel, maximum $50,000, and $1 in Pacific Oil, maximum there would be 60% of the $2 in oil, and that's $120. And then we have government bonds. Funds invested is $1 or 25% of steel, and the minimum amount the minimum amount is going to be 50 cents, 25% of steel. We've invested $1. So we have a feasible solution here, albeit not optimal. So let's go up to Data and Solver. And we put in our objective function, which is B20, the total return. We want to maximize that. We're going to change the decision variables, B14 to B18, the amount we invest, the dollars we invest in each one of the 5 investments, subject to our constraints. And that is that C23 is less than, B23 is less than C23, and then B26 to B28 is less than C26 to C28, and that B31, the funds invested in government bonds, is greater than or equal to C31, and C31, of course, is the minimum required. Again, it's a simplex. And we run our report. I'll go ahead and get an answer report for this one as well. And we can see that we invest 20,000 in Atlantic, 30,000 in Pacific, 40,000 in Huber Steel, and then 10,000 in bonds. This is a feasible solution, and our maximum total return given the constraints is $8,000. And if we look at the status variable column in constraints, we see that all of them are binding except the steel fund invested. We have a slack of 10,000. So this means we could increase the amount we invest in here by 10,000 if we had that additional funding. But the optimal solution is the one we're looking at right now. Okay, so let's continue on. Oops, let's get this up. Okay, so let's consider Foster generators as our next example. This is a transportation problem, and it arises out of planning for the distribution of goods and services from several source locations to several destination locations. And the quantity of goods available at each source location is limited, and at the same time the quantity of goods demanded or needed at each destination location is known. So we have, hold on Thomas, pardon me. Our objective is to minimize the shipping cost of goods from the origins to the destinations. And of course Foster generators is the example we're going to be looking at. And we'll bring that spreadsheet right up so that we can see it. And here is Foster generators, and we can see that we have origins in Cleveland, Bedford, and York, and destinations of Boston, Chicago, St. Louis, and Lexington. So the top table represents the cost of shipping from each origin to each destination. Cleveland to Boston, $3, Cleveland to Chicago, $2, Cleveland to St. Louis, $7, and so on. The decision variables are the quantities, and they're in the table underneath. And again, we have the quantity shipped from Cleveland to Boston, one, and I put some ones and zeros in, so Cleveland to Chicago and so on. So with those, we want to prepare a report that will tell us what quantities we should actually send. So this is the model. Our total cost is going to be B5 through E7, the cost for each location, times B17 through E19, that matrix, which is the quantity going from each source to each destination location. Okay, so this is our model, and this slide shows graphically the 12 distribution routes Foster can use, and such a graph is called a network. The circles are called nodes, and each origin and destination is represented by a node. The lines connecting the nodes are arcs. and each possible shipping route is represented by an arc, the amount of supply is written next to each origin node. The amount of demand is written next to each destination node. The total goods shipped from the origins to the destinations represent the flow in the network. The direction of the flow from origin to destination is indicated by arrows. So let's take a look at the solution for this one. And bring this back up. There we go. So take up our solver, go to Data, ribbon, and then far right is Solver. Click that. Now here our objective function is total cost. We want to minimize total cost by changing the decision variables, and in this case the decision variables are B17 to E19 in gray, the quantities we ship from each source to each destination. We do have some constraints. B20 to E20, which is the total amount shipped to each destination, must be equal to the demand at each location, B8 to E8. And likewise, the amount shipped from each origin, F17 to F19, must be less than or equal to the supply at each origin, which is F5 through F7. So those are our constraints. We'll go ahead and solve this one. Click OK. And here's the quantities we ship from each origin to each destination in the gray box to minimize our cost, and we're going to get a minimal cost of $39,500. Okay, next we'll take a look at using an analysis of optimization for advertising. Okay, so we're going to look at an advertising campaign, and it's this particular type of problem solution is designed to help marketing managers allocate a fixed advertising budget to various advertising media. They have choices and they want to know what quantity of each choice is going to maximize the reach, frequency, and quality of exposure. And so you're going to have restrictions that are set by company policy, contract requirements, and also media availability. So we'll take a look here. Relax and Enjoy Lake Development Corporation, as you know from reading the chapter, they develop lakeside communities at a privately owned lake. Their primary market includes middle and upper income families within approximately 100 miles of the development. And they've contracted an advertising firm to design the promotional campaign for them. So here we see the various types of media: daytime TV, evening TV, daily news, Sunday news, and radio. The cost, the customer reach is first. That's how many customers each unit reaches in them. The cost for each unit is there, $1,500, for example, for daytime TV. Availability is the number of slots you can get, and then the exposure. So these are some of the things advertisers are interested in, is reach and exposure. So this is where we have the coefficients that we're interested in regarding our advertising campaign. The decision variables are in this add placed. So I have a quantity of 1 as a placeholder for each one of the 5 types of media. And then based on the placeholder of 1, we get a maximum exposure, and that's in this case what we want to optimize, of B8 through F8. B8 through F8 is our exposure for each type of media, times B13 through F13. B13 through F13 is the decision variables or quantities for each. Now, naturally, we have some constraints. The reach has to be a minimum of 50,000 customers. Right now, with ones in each one of the units, we're only reaching 7,300, so this is not a feasible solution. We're required to make, by contract, a minimum of 10 television ads. Here we have only 2, which of course is going to be B13 plus C13. And we need 10. And likewise, our TV budget can be no more than 18,000, so we're good there. And the overall budget can be no more than 30,000, because that's all we have to spend. So we're good there. So let's go ahead and see how we've solved this with Excel by coming up to Data and Solver. So our objective function is B15 to maximize our exposure. Of course, we want to set that to max. Then we're going to do that by changing the variables between B13 and F13. Our decision variables are the quantities. Subject to the constraints that we see here, F13 through B13 B13 through F13. In other words, the quantities here have to be less than or equal to B7 through F7, the availability of advertising units for each one of those types of media. And then finally, B18 to B19 is the reach and the total number of ads. They have to be greater than the minimum required for those, C18 through C19. And then B22 and B23 have to be less than the limits that we've gone over. So we'll go ahead and click Solve. We do get a solution, and this is the optimal solution that we have in place for this advertising campaign. Okay, with that information in place, we've gone over a number of different types of models. Let's go ahead and take a look at problem 12.1. So go ahead and read through that one. I'm going to pause this and then come back in like 5 minutes or so, restart this, and then we'll go over the solution for problem 12.1, which will be similar to the graded exercise that you are required to turn in. Okay, so we'll go ahead and pause things for just a moment. Okay, so the Kelson problem is to maximize the money we make on the production of regular baseball gloves and catcher's mitts. So the profit we make for each is 5 times the quantity of regulars plus 8 times the quantity of catchers. We do have constraints. We have 900 hours available for cutting and sewing, 300 for finishing, and 100 for packaging and shipping. And we see the coefficients for our decision variables for each one of those tasks in the equations here. Let's take a look at Excel. So for the decision variables, the quantity shipped, I put in placeholders of 1 unit each. Of course, here's the profit we make on each, and total profit is going to be the profit times the quantity for total profit per each model. So we get 5 and 8 when we have quantities of 1. The objective function is our overall total profit, and that's going to be G3, the total profit for gloves, and G4, the total profit for the catcher's mitt. Here's the hours spent for each one of those gloves in the tasks of cutting, finishing, and packaging. So we conveniently put down here the overall hours used, which is just going to be the quantity times, for cutting, it's going to be the quantity of gloves times the hours it takes to cut a glove, the quantity of catcher's mitts times the hours it takes to cut a catcher's mitt. Likewise finishing, likewise packaging. Our available hours from our employees are 900 for cutting, 300 for finishing, 100 for packaging. So let's take a look at using Solver. So we'll go ahead and put this in place. Our objective function is going to be G5, which is our total overall profit. We want to maximize that, and we're going to do that by changing our decision variables, which is F3 to F4, our quantity of gloves produced and our quantities of catcher's mitts, subject to our constraints. B10 is less than B15. In other words, the finishing hours available is less than, the finishing hours used is less than the finishing hours available. The packaging hours used is less than the packaging hours available. And then the cutting hours used is less than the cutting hours available. And of course, we'll use the simplex algorithm, and we'll go ahead and get our results. So we get a maximum profit subject to those constraints of $3,700 by producing 500 baseball gloves and 150 catcher's mitts. Okay, thank you. This concludes Lecture 12.